Okay, welcome everyone to my webinar on a comprehensive introduction to piezoelectric and ultrasonic transducers. I'm going to be trying to establish and give you guys three kind of points of value. I want to make sure you understand how piezoelectric materials work. I've often found that people dreaming up new inventions. Although we always need inventors and dreamers, like sometimes piezoelectric materials cannot do the job. People try to or think that they can use them in areas that they will not be successful, or they may be already better technology. So I'll describe that, how piezoelectric materials work, what you can expect in terms of displacement and force and voltages and things. And also some of the microstructural reasons why they exhibit this force, charge, or voltage displacement relationship. Um, I will describe the differences from electromagnetic devices. I think definitely through this contrast, a lot of people, I've given some of these slides, presentation on some of these slides before, through this contrast, it really kind of starts to click as to when you would want to use a piezoelectric device or ultrasonic device, and when you might look for a different technology, such as electromagnetic technology. And also give an example of many different ultrasonic and piezoelectric applications. When using piezoelectric materials for devices, you have to be very creative, because as I'll show in the next slide, and the next, I think, slide or two, the displacement levels are really small. So in order to get it to do something useful, you have to be clever. You have to specifically target a certain type of phenomenon that is specific to that device. So I'll continue here. So one thing I want to describe is, one thing that is true is that having an understanding of piezoelectric materials and ultrasonic devices is not common. And one of the biggest reasons for this is that it's not taught in school. So it's not a commonly taught subject. Maybe in graduate studies there are taught, but not perhaps deeply understood, because basically there's a few reasons. One is that although there are many ultrasonic transducers out there, they do reside in specific niche applications. Although there's many niche applications that ultrasonic transducers are used, they do reside in some niche applications in comparison to, let's say, electromagnetic technology, with actuators and sensors, which are much more widespread. The other aspect about it is it does take a good amount of multidisciplinary knowledge to really appreciate the transducers. Each device specifically takes a lot of unique design constraints, and that isn't exactly an easy topic to swallow and really understand deeply in a few courses. So these are a couple of reasons why ultrasonic transducers and piezoelectric materials are not kind of commonly understood and known. It's also kind of seen as a black box, but I think a lot of folks have benefited from my YouTube videos and other things I've taught. And I think looking under the hood a little bit and getting a better understanding of this technology and these type of devices, it's not difficult, but you just have to spend a little bit of time and some hands-on work understanding. So let's take a look at, I didn't erase these markers, sorry, practicing the presentation. So there's a lot of different places where ultrasonic and piezoelectric devices are used. We'll just start with medical devices. So we have here medical ultrasound, where high frequency sound, ultrasound, is used to resolve different tissue, different problems in the body, diagnostics. In this case, it's a fetus. It's also used for welding, as you kind of see these markers on all of our masks that we have, or that we used to wear, or that maybe some of us are still wearing. All those little kind of markers are actually ultrasonic welds, and I think that's the only real technology that's being used for that specific application, for creating disposable masks. We also have a lot of consumer devices. In this case, I put a picture of a singing Christmas tie, which has like a small piezoelectric speaker in it. But there are also other, noise making machine, devices like in timers and other things that make a loud beeping sound. Many other applications in consumer devices, also considering the application of piezoelectric materials and haptics, like vibrations. It's very it's something talked a lot about in VR and sensing and interacting with our devices through feeling vibration and kind of smaller profiles. Another application, and I'm just like kind of giving some broad examples of where ultrasonics is used. And this is a huge area. I had an opportunity to work in a similar area for a while, which is in wire bonding or ball bonding. So we have a IC here, but the black part of the IC is taken off that plastic cover. Well, underneath it, there are, semiconductor, devices, which are then connected through these leads from these small wires. And what's used to bond those wires from one platform to another? Well, that's ultrasonics, ultrasonic welding, kind of on a very small scale. It's called wire bonding, and in a smaller scale, it's called ball bonding. And one of the maybe original applications of ultrasonics was, I want to give the number 1916, the device created by Langevin, which is now called Langevin transducer. It was used to detect submarines in World War I and also World War II. So that was actually where quartz crystals were sandwiched in between steel plates, and were in those pulse echo system was actually used to detect submarines. That was one of the original ultrasonic transducers kind of practically used. So it's kind of interesting. And even till this day, ultrasonics remains a very interesting area for naval research. My PhD was actually funded by the Office of Naval Research here in the United States. So it's still a huge interest area for that sector. Although it's not really used for kind of attack or destruction, it's mainly used for sensing, like submarines, or sensing other objects underwater, and other applications like that. All right, now shift one slide for my company, and then I'll kind of get back to the presentation. So about Ultrasonic Advisors, I founded this company in 2019. I'm the founder and lead consultant of it. My experience areas are in many different types of transducers, but I have focused in both clamped Langevin transducers. But there's many other types of devices I mentioned here. I kind of got my start from my YouTube channel, and that's how I got my first client, and I realized it provided great results. So I should continue this forward and continue providing this service to companies who don't have in-house experts or in-house resources and experience in this area, so they can get their products to market sooner and also fix the problems they may be having already in their present products. I have expertise in finite element simulations using COMSOL for these ultrasonic and piezoelectric devices, but I also have many other expertise areas that come in handy for helping clients out in their projects. So the best way to get in touch with me to understand if my services would be good for your project would be to schedule a consulting call from my website. You can email me at hussein@ultrasonicadvisors.com, and you can also join my email list. And all of you all, as part of being on this webinar and signing up, you are part of the email list. All right, so I'll give a introduction for piezoelectricity finally, and I'll describe what piezoelectricity is, its definition, and then I'll describe two cases of piezoelectricity. Piezoelectricity, in the aspect of being piezoelectric, it's called a smart material. So there's a coupling in between these two phenomenon. So piezo in Greek means force, and electricity refers to charge. So the basic idea and the function of a piezoelectric material is when you compress it or when you change its shape, it generates charges on the surface of the material. And those charges, will produce a voltage because the piezo is a capacitor. So you could think about it as producing a voltage as well. And also the opposite is true too, because this is a smart material. The opposite is true, is that if you provide a voltage, you'll generate charge, and that will also then expand the material or contract it depending on the polarity. So it has this very tightly coupled behavior of charge and pressure, and also voltage and displacement, and also then it can generate force. So those are very tightly coupled, and they come from the exact same phenomenon. This is opposed to something like, let's say, the thermal expansion effect, that if you heat a material, it grows in size. But if you pull on a material, it's not going to start heating up in the same way that came from thermal expansion. That's not a smart material. That's not a smart effect or a smart material effect. However, piezoelectric materials are very coupled in those two domains, and that same phenomenon occurs from the piezoelectric effect, what we call the converse, which is applying a voltage and getting a displacement. That the same phenomenon that causes the pressure to voltage effect. So I want to give this slide is also to give a bit of a reality check in terms of what voltages and displacements we can generate. And then I think hopefully maybe some light bulbs and some thoughts will definitely come up after this discussion. So if we provide, and you know, I usually provided this as a PowerPoint slide where I step through the answers and I ask questions, but I'm trying to get through a little bit quickly, just to make sure we have time for the rest of the presentation. So if we provided 1,000 volts on a piezoelectric material, let's say this is a blue piezoelectric material. They don't come in blue, by the way, but they come in like you don't even really choose the color. They usually are either yellowish or grayish, but basically you provide a voltage of 1,000 volts on a piezoelectric material. Let's say about 4 millimeters cubed or 1 inch cubed or something like that. And what displacement would you expect? You know, would you expect 4 millimeters or all the way down to 0.4 microns? And the actual answer is 0.4 microns of displacement by providing 1,000 volts. To a piezo ceramic. So that's quite a small displacement. One might think like, what am I supposed to do with 0.4 microns? We should think of millimeters or feet or something like that. This is extremely small. So you do have to be quite clever in how you apply piezoelectric actuators to really do something in the real world that's practical, that you can actually use. Besides nano displacement, obviously nano displacement you could do already with this voltage and this displacement level, but you can't do much more than that. So the second question is the direct piezoelectric effect, which is when you apply a pressure and you get a voltage coming out. So if I were to stand on, you know, converting my approximate weight into newtons, now it's like conspicuous. Nobody knows how much I weigh now, because anyways. So 4 millimeters thick and 8 millimeter diameter sample. If I stepped on it, then it would provide approximately 1,800 volts. So this is quite a large voltage for that. Obviously, everything would work out in terms of the physics. Like I would step on it and the material compresses, and that the energy that's stored elastically cannot be more than the energy converted electrically. So there's everything balances out in this kind of whole system, but it's a way to convert energy. And yes, you don't get more energy to convert to electrical than you actually put in mechanically, you know, force displacement and putting that in. But you can actually generate a good amount of voltage from somebody standing on it, but usually that's not the signal that you're kind of going for. If you don't have such a nice kind of signal happening. And this is just a example in this kind of oscilloscope probe that I'm hitting the sample and it's kind of generating voltage. There's like a piezoelectric element, and I think actually this is that element here. Now I'm going to switch gears, and we're going to start talking about piezoelectric transducers versus let's say traditional in this case, it would be a sensor because it's a microphone. So if we're comparing a piezoelectric microphone to a condenser microphone, and now this discussion is a little bit simplified and a little bit weighted in terms of my favoritism right now to piezoelectric materials, especially given this presentation. But if you just look at these diagrams and nothing else, what you're going to notice is there's just so many components. There's like this, in this case, there's a 9-volt battery source. There's like this resistor here. There's a capacitor there. This structure seems kind of big, like this microphone structure where you have the flexible plate and the rigid plate, and we have a ground. It seems kind of complicated and has many components. That being said, we look at the piezoelectric, you know, schematic, and we just see one component. That's a crystal, which is usually represented for a piezoelectric device. So really we can get a much more simplified device and technology, even though in comparison to using other technology. Now this would have other benefits, you know, for example, frequency response and let's say quality of the sound. But if we are really looking for simplifying our device, maybe even miniaturizing it, further, and especially getting the cost really low, number of components is a huge deal, and complexity is a huge deal in that sense. So piezoelectric materials are a lot more simple, and it can directly generate a voltage you can use. As in this case, you need a couple of components in order to generate a proper output oscillating signal. And feel free to ask any questions in the chat. So in this slide, I'm going to go over the origin of piezoelectricity. Do all materials exhibit piezoelectricity? And the answer is no, very few do. And another question, do the materials that exhibit piezoelectricity, do they occur naturally? The answer to that is yes, some of them do occur naturally, like quartz, but they have such low properties that we no longer use them. They were the first ones discovered. They were the first piezoelectric materials used. That was the first one used in the first Langevin transducer was quartz. However, now we have a material called, and this is the most commonly used piezo material. It's also ceramic, so it's brittle, as you can imagine, but it's also very tough at the same time. So we have different methods to apply it, but it's called PZT, and it comes in different forms. But the base kind of you can say composition is the same. But kind of stepping back, so piezoelectric materials that we use in all of our applications do not occur naturally. So you're not mining piezo materials. You actually get the basic, oxides, and there's a bunch of different processes, solid state reactions that you go through in order to create your piezo ceramic. They do also come in polymers and also in single crystals, but for our discussion today, I won't describe that. So on these two sides, I'm comparing two types of crystal structures, and one of them represents symmetric crystal structures, where every kind of atom as a whole, if you count everything together, that you're not going to have that the center of positive charge and the center of negative charge are the same. So we call this like a central symmetric crystal. It's like everything is kind of, happens in even patterns. And if you drew that in a kind of 1D format, you would draw ions. So you draw positive ion, negative ion, positive ion, and they all have about the same bond strength between them. So you draw that as a spring. So when you apply an electric field, let's say we have a positive terminal here and we have a negative terminal there. The positive ion goes this way and the negative ion goes that way. We have approximately canceling, we'll have canceling displacements. So the amount that the negative ions will move will be then canceled by the positive ions, and that system will repeat. So you'll get no net displacement. However, it's very true that the individual ions will move, but they won't all move in a net displacement level. Now, if you look at piezoelectric materials, which you notice there's like this, titanium ion kind of sitting off center, that is actually the key to having piezoelectricity, non-central symmetry, as it's called. But basically, this crystal structure is not symmetric, which then causes alternating like bond strengths because the distances between ions are different. So the alternating bond strengths. So really, you're not going to get the same, you're not going to get canceling oscillation. So as a kind of as an example here, I have these big springs and these small springs, like the big spring here and small spring there. And the big springs are, let's say, tough. Let's give an example. They're strong, so they're only going to allow compression, like let's say of delta L. And the small springs are going to create expansion of 2 delta L. So because now they're no longer canceling because the differences in bond strength, because the physical separation distances, now you're going to have net displacement. Now you're not going to have 2 times the displacement in one kind of structure than the next. But that's just for an example. You have more displacement in one area than the other, and that causes piezoelectricity. And that, and this is obviously, as I mentioned, it's not true in almost all materials, but in a certain class of materials called non-central symmetric materials, and specifically in the ones that we use are not found in nature. They are created in the laboratory. So jumping back to this example of piezo versus electromagnetic, this is an actuator case where we have piezoelectric materials use as an actuator, or in this case, a speaker. So the question is there a bond between the lead and the oxygen ions? Yeah, so everything is bonded. Everything has its own is bonded together. Well, yeah, so that's true. Yeah, there are kind of bonds between each of them, and now there are kind of theoretical ways you can map it out and try to understand it a little more closely. But in general, in an ionic system, ionically bonded system, you do have bonds between you know, ions of different polarity in the same structure. That's what I'll say there. So actuators, let's continue there. So we have the same device here. So the same device is a actuator and a sensor, and that's kind of true electromagnetically. Like if you actually actuated a speaker cone on purpose, you may have some signal coming out of electrical leads. We know that you have to optimize for one case or the other. So if even for a piezo device, you'd have to optimize it to be an actuator or optimize it to be a sensor. But the differences aren't as, let's say large in some cases. Again, you do see the simplicity of a piezoelectric device versus an electromagnetic device, which requires a permanent magnet and a coil, which can be both very heavy. So we see this weight aspect coming in. We have this alternating voltage, an AC voltage required for an electromagnetic device, and lo and behold, we do require an AC voltage to provide a piezo. A common misconception is that you just provide a voltage to a ultrasonic device and it starts resonating. That's not true, although it may seem like that because the packages you get maybe have a built-in electrical oscillator that when you do power it, it starts there's oscillating electrical signal converted, but that's not how the basic device works. You actually have to provide that circuit, which is sometimes in the same casing, but it is a different circuit which provides AC signals. Another thing we see here, besides just the size and let's say the mass, is coils. So we have current-driven devices. So electromagnetics are current-driven. Piezos are voltage-driven. What this also leads us to is in terms of power. So as you decrease, we know that as we decrease the size of a wire, the resistance goes up. So if the wire size goes down, basically if you shrink an electromagnetic device, the wire size has to decrease, and that drives up the resistance. The resistance increases. The resistance stays the same, but the resistivity is the same, but the resistance increases as the wire diameter gets smaller, and that's where it's really advantageous to have a voltage-driven device, because piezoelectric materials and their devices don't have a functional limitation on size, because you just have to provide voltage, not current, because current in a small wire is generally going to start creating heat, and that's one of the reasons why where piezoelectric devices shine is when you need small devices that are efficient and effective. And obviously, when you're making something really small, you can't make it very complex. That's also another area where piezoelectric materials shine, where you need smaller devices which require higher efficiency and low complexity. But if you want larger power, now you're looking at electromagnetic devices such as large speakers. However, piezo speakers are used for their high frequency response because their simplicity. They can be made in such a way that they can have a higher frequency response than an electromagnetic speaker. That being said, for kind of high power delivery, electromagnetic speakers and electromagnetic actuators are kind of the only way to go. It also doesn't create a natural way for there to be large displacement, like a metal or this permanent magnet or a moving stator can move kind of infinitely through a coil, whereas that same phenomenon is not really true. Like with piezo devices, you are physically actuating. The phenomena is not happening through air. So like electromagnetic fields are occurring through air, you're not providing voltage through air to a piezo device. That's not going to work. So some of you may have seen this kind of cartoon that I made. Somebody asked, I heard ultrasonic motors are efficient. And I said, that's true. They are very efficient. But can you make one for a car? And the answer is no. Because for several reasons. One is the power. They won't, there's not a topology that will simply provide that much power for propulsion. They don't scale very well, so you can't make them large because many of these ultrasonic motors, they work off size. And that dictates their resonance behavior. So you can't make them large, and you can put like a bunch of small ones together, but that just makes it more complex, which defeats the purpose of using piezo devices. They're also slightly fragile. They're brittle, so that has to be taken into consideration when looking at piezo devices. Let's see, is there any other reason why we can't use one to propel a car? If you have any other thoughts about it, you can put it in the chat, and I'll read it off as to if you have comments as why can't you make an ultrasonic motor for a car? And also, like, when the frequency goes down because you made it bigger, and now you can start to hear it, and that's not going to work. If you have a big old chunky ultrasonic motor that like works at like 6 kilohertz or something like that, that's not going to work. That's going to be like a huge speaker. And yeah, if you have any comments on that, like, please feel free to put it in the chat, and I'll read that off. So there's so many applications, and each one of them uses a different aspect of ultrasonic motion. So there's non-destructive testing, which uses high frequency ultrasound to kind of, in a simple format, it's kind of a pulse echo kind of way. You send out a wave through a material, and if it comes back in a certain way, in a certain fashion and frequency, then there's like a defect at a certain distance in your structure that you're trying to test. You have ultrasonic cleaners, which uses power ultrasound and which creates cavitation. So specifically targeting a specific phenomenon, cavitation, in order to provide that cleaning effect. There's dental equipment used, for example, surgery. So that uses ultrasonic mechanical resonance that the surgeon or the dentist can provide a small force, but it really cuts really well and easily because it provides high acceleration and high, globally there's low force, but locally there's a huge amount of force. That's what happens when you have high acceleration. There's an atomizer which also uses ultrasonic mechanical resonance. We have pressure sensors, which uses the direct piezoelectric effect. MEMS, many MEMS devices are either capacitive or they're piezoelectric in terms of actuation, because you can't really make electromagnetic devices in a clean room fabrication level on the micron size. So you have to use, deposition of piezo ceramic material or piezoelectric material onto your, let's say, silicon wafer, and do all of your etching processes in order to create such a device. You have to use piezo for that. Inject printer. It has a fast mechanical response in order to eject the fluid droplets. Diesel fuel injector, it has a fast mechanical response with high force. So now we're not looking at ultrasonic, we're just looking at high force and fast mechanical response. And because the simplicity of the devices, you can make them compact, efficient, but also they react very quickly, because the more mechanical components you have hanging around, the response time goes way down. Goes way up. So for a fast response time, you need a simple, compact device due to the mechanical constraints. For manufacturing, as I mentioned, drilling, bonding, welding, we use ultrasonic mechanical resonance to like melt two materials together or weld them together using different phenomenon. Nano and micro positioning. We use the converse piezoelectric effect. You apply a voltage, like you increase your voltage by 1 volt, you get like a portion of a nanometer displacement. So you have very fine control of displacement, which is obviously important for specific applications. Now I'd like to introduce another way of arranging our piezoelectric actuators. And we have force and displacement are the two things we look for when we talk about actuators. So in this corner, we have high force, high displacement. In this corner, we have low force, low displacement. And that's not, low force, low displacement is not really relevant for this case, because bare piezo crystals start with very low displacement, as I mentioned. Like they start with 0.4 microns by putting 1,000 volts on them, but they have very high force. In order, if you were standing on that disc, you would go up by 0.4 microns, kind of guaranteed. Like it would move you, but you couldn't tell that it's actually moving you. But if you do need low force and low displacement, high force, you can even use a bare piezo crystal in different orientations. Now for high displacement, high force, we have a couple of options. We can use an ultrasonic resonator. So I mentioned that we have 0.4 microns of displacement when we apply 1,000 volts. However, using ultrasonics in a resonance format and also providing a specific shape to your device, the additional components added, you can increase your displacement by up to 1,000 times. So now you have 400 microns of displacement instead of 0.4. Now we can now there may be, usually you get up to 100. That's kind of typical in some applications, but you can get up to 400 microns or half a millimeter of displacement, and you provide a particular phenomena that you're going after, like cavitation or welding or for example, those two phenomena, then or cutting. Now you suddenly have a very effective device. On the lower frequency side, multi-layer actuators, where you stack a bunch of piezoelectric materials together, like 100, let's say even up to 100, let's say, or more, then providing a voltage actually increases the electric field. So piezoelectric materials aren't, you could say, voltage driven, they're electric field driven. So if you actually provide a lot of layers, the layers get thinner, so the electric field goes up for the same voltage, so you actually get much more displacement. So in that example that I showed, if I had 1,000 layers, we would have 400 microns of displacement, although there's a limitation on how much actual, what the strain can be in the material before it fractures. So for high force, high displacement, low force, which is a little bit more on the economical side, we have bending actuators where you bond a piezo material to a thin metal substrate. So when it actuates, instead of just expanding or contracting, it bends. So bending, you get a lot more gain, you could say, or adding up or integration of your displacement at the tip. If you couple compliant mechanisms, so if you push a little bit this way, but you have some type of lever system to increase that displacement, that also helps significantly. Also, piezo polymers can provide high force, high displacement, low force, also very naturally too. All right. Next slide. So there's two types of ultrasonic transducer applications. Also, here's another way of looking at it. The first is where the goal is ultrasound, where you need, in this case, in medical diagnostic, you need that wavelength to be small, so you have to increase your frequency. In ultrasonic welding, you need ultrasonics in order to provide the localized heating effect or other phenomenons that are associated with welding to occur. You need that fast vibration. That's actually the output of the device. At the end, there's no more transformation happening. Also, surgical devices, which both provide a jackhammer effect and also a cavitation effect to the tissue that you're doing surgery on. This is where the goal is ultrasound, is ultrasonic oscillation. There's also transducers where the goal is not ultrasound. So that could include ultrasonic motors, where you have, let's say, a motor. Let's say this hand is an ultrasonic actuator moving back and forth, and this is a stator. So every time the ultrasonic device actuates, it moves the stator just a little bit. And that output, you're looking more from a linear output, like from your stator. The device is not exactly, the goal is not ultrasound. The goal is linear movement of the stator. And also piezoelectric transformers, where you couple different types of piezoelectric transducers together in a certain format, where you can provide a small voltage going in and really step up the voltage in a very efficient package, or do the opposite, where you provide a large voltage, let's say, and then you would step that down to something that you can use for that particular application you're looking for. So for these cases where the goal is ultrasound, you have almost no choice as to whether using a piezoelectric device or not. You have to use a piezo. So this is definitely a piezo device. But if the goal is not ultrasound, you can look into other types of devices, like for rotary motion, for a car, you can, or for speakers. Let's say if you're not using precisely ultrasonics, you may be able to use, especially for the car or the motors or actuators which have a large length, like you probably would not or long stroke length, you wouldn't really use a piezo material. At least you have choices, especially when people are inventing ultrasonic devices. They should look at whether the goal is ultrasound, or if it's not ultrasound, you have to be careful as to whether you really need to look at whether you really need an ultrasonic device or piezoelectric device. But in these two cases, they work beautifully. Why? Because they are compact devices. The goal is to be compact. And that is where they excel. That is where the piezo excels over electromagnetic. Compact and simple, and efficient at that. So I'll just describe a couple of applications. So here's an ultrasonic resonator, which goes into a phacoemulsification handpiece for a cataract surgery. You put a needle at the tip, and here's kind of a simulation of what it looks like. Here's a kind of a half cut of that. It's also, the piezoelectric transducers or ceramics are driven. There's high amplitude at the tip, and there's a lot of gain due to both resonance and also the necking down of this oscillation to a tip. The ceramics are compressed, so this tells us one thing, that ceramics don't excel under tension. You need to provide compression to them if you want to get the best performance, because once they get under tension, they will readily become nonlinear, and they'll also crack. So this is an extremely common topology where you bolt a piezo stack together, and you provide a horn for amplification purposes, and use the resonance behavior. This is a very, very common topology for many of the applications that I mentioned, especially power ultrasound, where you need that. Here's another one, a very simple application where we have a igniter. So how does the igniter work? So the basic piezo equation is that charge equals the force times the piezoelectric charge coefficient D. And we also know this about a capacitor. The piezo is a capacitor, so the charge equals the capacitance times the voltage. So if you make a capacitor thicker, you drop the capacitance. So in this case, if you drop the capacitance and you're generating a set charge, the voltage has to increase. So the Q is about the same. If you provide a set voltage or a set impact, you're dropping the capacitance, so the voltage here has to increase. So that's how you can generate sparks from a simple kind of igniter, which creates an impulse force from a loaded spring onto your ceramic, and that then will create your large voltage that you need to ignite your flame. Here's a bending transducer. In order to get that 0.4 microns to do something for you, you bond a thin layer to a passive layer, and as the piezo expands, the device bends in different ways depending on the polarity of your voltage. This produces large displacement and low force. It has a low response time, but they are very useful in many applications, like the buzzers are all this type of device. And there's some very kind of high-tech devices like atomic force microscopy, which uses that. There's also many sensors, ultrasonic motors, and we know this very classic example of this distance sensor, which I'm sure all of us have seen in some shape or form, which are also used in our cars. Many cars have these sensors. This also uses this bending format in order to couple better with air, because for air, you need to move a large surface in order to couple and provide any significant amount of energy to it. In order to get large displacement, you can use multi-layer devices. So you layer several or hundreds of layers together up to, and because electric field drives piezoelectricity, not precisely voltage, if you look at the equations, making the layers thinner provides the same voltage for thinner layers, which provides effectively more field, which you can get more displacement, but there's always a limit until the device will crack. So that's what you have to consider there. So here's some industry trends. A lot of what's being talked about is lead-free materials. I don't, as far as I know, we're not precisely there yet. There aren't PZT, the material I mentioned, which is used in almost all applications, has lead in it. It's oxidized, so it's not particularly dangerous in its final state, but that doesn't change the fact that that lead does occur, or is there in its processing, and is potentially there as a hazard. But I think we're still some ways away from that, because there hasn't really been a comparable material to PZT. And just in general, because I'm a consultant, so I encounter a lot of new device. I can encounter a lot of old devices which are being made for new constraints, new topologies, but I also find a lot of new application areas that for example, ultrasonic knives for consumer use. And this was an interesting one I found recently, and these are not companies I've worked for, by the way. So these are not so it's an ultrasonic surgical transducer which is guided by ultrasound, so it's kind of using ultrasound in two ways. So that's kind of it's an interesting device, using ultrasonics for cooling, let's say in a compact fashion, like here. And also ultrasonics for cell processing and and diagnostics for biological testing. It's a really it's a very kind of up and coming process. It's already actually it's in production in certain diagnostics to improve performance. So cell processing, being able to handle small particles with acoustic waves and microfluidic domains. So there's a lot of new inventions. I think a lot of space to invent and to create new devices. I think it's definitely not saturated, but many of them are reinventions of older technologies, but for new constraints and new applications and new needs that are occurring now. So with that, I will finish my presentation and open it up for questions, and I'll stop my recording. And